is continue. The determinant of a matrix is denoted by the dt of A or within the single line or modulus of A. So we read it as determinant of A. So if a square matrix of size n cross n, then what is its determinant? So here I'll take up a 2 cross 2 determinant, so which is a square matrix whose order is 2. So A is equal to A, B, C, D. Then what is its determinant? So it is very easy to expand. So from the diagonal entries will be multiplied, AD minus opposite diagonal entries will be multiplied. So the cross product AD minus BC so gives the value of the determinant. Similarly, we'll multiply, we can find a determinant of A3 cross 3 matrix. So here I have written the example. Next, let us moving on to the properties of determinants. So we have some 9 to 10 properties of determinants. So let us discuss one by one. Because properties will play a very important role for solving the problems. So the first property is the determinant of identity matrix is always 1. So here I have taken one example, that is I have taken a 2 cross 2 identity matrix whose expansion is 1. Similarly, I have taken one more example, that is a 3 cross 3 identity matrix. Then its determinant is always equal to 1. So according to this property, so when we expand or when we have to find the value of an identity matrix, so the value of a matrix is nothing but the determinant. So it is a scalar number, right? So determinant of an identity matrix is always equal to 1. Is always equal to 1, whether it is of order 2 or 3 or it is of nth order. So determinant of I is always equal to 1. So this is the first property. So the second property says the determinant changes sign when two rows or columns are exchanged. Then the sign of the determinant changes. So before expanding the determinant or before finding the value of the determinant, if we exchange the rows or the columns, then the value of the determinant gives by changing its sign. Here I have taken one example. Let A is equal to a matrix of order 2, which is A, B, C, D, and its determinant gives AD minus BC. Determinant of A is AD minus BC. So let us exchange the rows of this matrix. So we call this operation or this property as row exchange property. So after exchanging the rows, we'll get an equivalent matrix. Let it represented by A1, which is equal to CD AB. So R1 changes to R2. So let us find the determinant of A1, which gives BC minus AD, which simplifies to minus of AD minus BC. Since AD minus BC is the value of the determinant A, so we can write this as minus of determinant A. So according to this property, now we'll arrive at determinant of A1 is equal to sign change minus times of determinant of A. So whenever we want to change the rows or columns of a matrix, then the determinant changes its sign. And here I have written one sentence like determinant of every permutation matrix is always equal to plus or minus 1. So we'll discuss about the permutation matrix in the next. So the third property is if two rows of A are equal, then the determinant A is 0. Okay. So without expanding the determinant, we can write its value as 0. If whenever we find the two rows are equal, then without expanding the determinant, we can write its value as 0 by using this property. So here, this property is called as equal rows. So let A is equal to a matrix AB, AB, whose rows are equal. So without expanding, we can write the value as 0. So after the expansion also, we get AB minus AB, which is 0. So without expansion, we can mention its value as 0. So the next property is, if A has a row of zeros, the determinant is 0. So this property is called 0 rows. So if we find any row of a matrix is completely 0, then without expansion, we can write the value of the determinant as 0. The next property is called as the transpose rule. So this is very much important. So the value of the determinant remains unchanged if its rows and columns are interchanged. So if determinant of A is equal to transpose of the determinant. So if the matrix A is transposed, then the value remains same. Determinant of A is equal to determinant of the transpose of the matrix. Here I have shown this property in a 2 cross 2 determinant. So the next property is with respect to singularity. So if A is singular, then determinant is 0. And if A is invertible or non-singular, the determinant is not equal to 0. The next property gives the product rule. So the determinant of AB is the product of determinant A times determinant B. So determinant of AB is equal to product of their determinants. So this is a very good property. This is called as the product rule. See here I have shown an example. Okay. So a particular case of this rule gives determinant of A inverse. So it is denoted by determinant of A inverse. So always what we consider 1 by A as A inverse, or we write A inverse as 1 by A. So in the same sense, from this rule, we can consider determinant of A inverse as 1 by determinant of A. So with respect to A inverse, so which gives identity. So determinant of A into determinant of A inverse. So matrix, I have given this property in matrix multiplication. A into A inverse is always equal to I. So in the same sense, determinant of A into determinant of A inverse is equal to determinant of I, so which is equal to 1. So let us combine the properties 8 and 9. So determinant is linear in each row separately. I will tell you the example. What do you mean by linear in each row separately? So the determinant depends on the first row. So here I have taken an example. So suppose if I have the 3 matrices of same order ABC. So this rule says determinant of A is the same combination of determinant of B and determinant of C. So linear combination involves 2 operations, adding vectors and multiplying the scalars. Okay. So this rule can be split into 2 parts. So one is adding vectors in first rows, then multiplying by scalar in first row. Okay. So see, the first row is a linear combination, A plus A dash, B plus B dash. The second row is CD. Okay. So we have the determinant of A plus A dash, B plus B dash divided CD. So which can be written as A B C D plus A dash B dash C D. So according to this rule, we are getting one determinant, that is determinant of A is equal to determinant of B plus C, which in turn is giving the sum of the two determinants, that is determinant B plus determinant C. Similarly, multiplying a scalar in the first row, determinant of TA, TB, CD, which can be written as T times of A, B, C. So that is determinant of TA is equal to T times determinant of B. So we can take out that scalar from the rows. With respect to this property, we have one more property, that is subtracting a multiple of one row from another row leaves the determinant unchanged. So here I have taken one example. Let A is a matrix whose order is 2, say A, B, C, D, and B is a matrix of order 2, A, B, C minus Ka, D minus Kb. So determinant of A is AD minus BC. So finding the determinant of B, which gives the same value as the matrix A. So subtracting a multiple of one row from another row leaves the determinant unchanged. So this property will help us for the row transformation. So whenever we use the row transformation, we'll be adding or subtracting the rows with some scalars. Then the value of the determinant remains same. So with respect to these properties, here we have one theorem, so which is very important one. So for every square matrix A, where A is a k cross k matrix, means which is a square matrix, and for any scalar alpha, then determinant of alpha times A is equal to alpha to the power k determinant of A. So that scalar takes the power as the size of the matrix times determinant of A. So this is very easy to evaluate. And the last property is with respect to the triangular. So if A is triangular, then determinant A is the product of the diagonal entries. So if the triangular A has ones along the diagonal, then always the determinant of that matrix is equal to 1. So here I have shown the triangular property both in upper triangular as well as in the lower triangular. So whenever we have a triangular matrix, then without the expansion we can write its value as the product of the principal diagonal elements or simply the diagonal elements. So all singular matrices have 0 determinants. See, you go through all the properties, try to understand. So I have given each example to all the properties.